Hello, everyone. I'm Zhao. I'm a research scientist from the PyTorch Prof Infra team at Meta. Today, I'm going to talk about TorchBench regarding the performance of PyTorch ecosystem with continuous benchmarking. First, I will talk about a bit like principles of TorchBench. So first is we want to maintain a suite of state-of-the-art models that is always runnable on the latest PyTorch nightly release. Sure, PyTorch has a lot of unit tests to guard its functionality and performance, but still we feel that the unit tests are not sufficient because we require some integration tests to combine PyTorch and many models together to make sure that its nightly release works on these models. This is very helpful to capture the failure early on the nightly level to avoid any negative surprises that could affect the stable release. And secondly, because we are going to deploy all these models on the nightly level, we cannot run them end-to-end. Right? Running them end-to-end means we need very large capacity. We need maybe a distributed cluster to train these models for hours. This is not something we want to do in the performance CI. Therefore, we have to adapt the models to slice them in the so that they can run on a single GPU or a single node. And also, we want to make sure the performance signals are both stable and fast, ideally within a couple of minutes. And thirdly, besides testing the default or the PyTorch 2.0 compile performance result, we also want to demonstrate the coverage and gain of experimental PyTorch features or new hardware devices. Overall, the goal of TorchBench is that we want to build reproducible benchmarks. We want to be transparent and open about our benchmarking results so that the logs are available and the performance benchmark metrics are available as GitHub artifacts. And also the results are shared through the PyTorch HUD dashboard. This is very important to us. Over time, we have seen pretty good growth on the contributions of TorchBench. Starting from 2022, we have grown our number of models from around 50 to now it's over 113 open source models. And it covers a lot of different machine learning areas like NLP, reinforcement learning, text generation and translation, etc. And we also see pretty good growth on the number of commits of this repository, which is located at PyTorch/benchmark from both Meta and non-Meta contributors. We also have a Docker release, which is based on the nightly PyTorch release, so that we will test if TorchBench models are runnable on the latest PyTorch release. If it breaks, we will investigate whether it is PyTorch's problem or it is TorchBench models dependencies problem. Right? After we triage it, we will submit PR to fix it. We are currently maintaining this repository to make sure that it is always up to date with the latest PyTorch nightly release. Actually, we have fixed a couple of bugs that from our dependencies of these models, so that they can respond their incompatibility with PyTorch nightly release as soon as possible. So this is a graph of categorizing the contributions of TorchBench in the last months. In September, we have 40 commits from Meta, 9 commits from non-Meta. And for the non-Meta commits, they are from Intel, NVIDIA Torch TensorRT, RevoSync, and GraphCrawl, respectively. And all these data are collected from the public GitHub profiles of the commits. Okay, so this is an important slide. We really stress the composability in TorchBench. So we compose everything on these 5 different dimensions. The first dimension, of course, it is the model inventory. We are trying to we are collaborating with many parties to make sure our model inventory is up to date. We are both having the classic CNN models and the newest large language models, but these models will be sliced so that they fix on single GPU, so that they can be used in the CI. And for model transformation, this refers to many compiler and backend techniques, such as PD2, torch.compile, torch TensorRT from NVIDIA, and also CUDA graph, AOT inductor, and extra. Yeah, we encourage people can contribute to TorchBench so that it can support even more compiler backends. And third dimension is input transformation. On this dimension, we support many input-related customizations to the model. For example, input batch size. Some models doesn't support input batch size, such as a couple of reinforcement learning models doesn't support batch size. But yeah, for those that support it, you can do that. And also, we support different precisions on the sample model inputs, and also the channel last. And fourth dimension is device. We support running our models on different hardware. But this will require contributions or collaborations with hardware vendors. Currently we support CUDA, AMD GPU, CPU, and Apple MPS. And finally, the last dimension is the performance metrics we support. So first, we support numeric accuracy. By accuracy, we mean because we cannot run end-to-end, right? Because it's too slow for CI. So for accuracy metric, we will compare the TorchBench result on, for example, if we will compare the output tensors of torch.compile with the golden standard, and we use the default PyTorch 1 eager mode on float 32 as the golden standard of the numeric values, right? And then we compare if, say, the PD2 version of the output tensors are, too close or are closely enough with the golden standard. And of course, we support the QPS, or the per iteration latency of the test. And also we support memory-related metrics such as peak memory usage, including both CPU and GPU memory usage. And we also support flops counters, supported by the torch dispatch flops counter, so that you know roughly how much GPU flops can be achieved on this model. And we integrated with PyTorch profiler, so that if you run a TorchBench model, you can output a PyTorch profiler traces that can be visualized on a TensorBoard, right? And then you can look at the TensorBoard traces to see the GPU utilization and among other more detailed metrics. And last but not least, we have very good collaboration with PD2. It will tell you that how much time it takes to compile this model and how many graph breaks, right? And based on that, you can design the test that say, okay, I don't want my model to have more than, say, 2 graph breaks on PyTorch 2, right? This will be integrated into PyTorch CI so that the performance of your model can be guarded. Yeah. So with all these composabilities on these 5 dimensions, we can users can easily know the answers to the questions such as what is the performance speed up of NLP models, right? On PyTorch 2.1 versus 2.0 with torch.compile, or you can easily know the flops results on NVIDIA A100 GPU on Llama 2 model with and without CUDA graph. Yeah. And because all the tests are very fast, can finish in maybe just less than 3 minutes, right? We design very good, like we make sure that it's very easy to use. So first choice is you can just clone it from GitHub and install a model, and then use this run.py driver to run just single model on CUDA train test. Or the second choice is you can pip install it as a library, and then you can import it in your own benchmarking script. Yeah, it will get the same result as run.py. Yeah, and the third choice is if you want to, a bit deep into this framework, and you want to deploy your benchmark into PyTorch CI, right? Really want us to do integration test on your model, like on a nightly basis. You can write a user benchmark and make a PR to TorchBench. And this has many benefits. So first, if you deploy it into a CI, we will run it continuously on a nightly basis to make sure it works on the nightly PyTorch release. And second is we will run a regression detection script on your user benchmark. Say, okay, today's metric, does it regress or does it improve comparing to yesterday's PyTorch release? And if we detect regression, you have the option to create a GitHub issue on this TorchBench repository, and it will send notifications to the benchmark owner, okay, telling you that this we have captured a performance signal. Yeah, and finally, we also add the bisection support on user benchmarks. Say if there's a regression detected, and you really want to know that which specific commit that causes this signal, you have the option to run a bisector, which is simply a binary search on between two PyTorch commits, and it will try its best to figure out which PyTorch commit that causes this performance signal. Okay, enough about how to use TorchBench, and next we will talk about how to contribute to TorchBench. First, yeah, we welcome you to add new models to this repository, but we also set a limit on the train and inference test. Usually it should finish within 1 minute. Yeah, and yeah, maybe your model is from a very large setting that runs on multiple GPUs and a cluster. Like, unfortunately, currently, our CI infrastructure only accepts single GPU tests. So you may need to slice your model, maybe shrink it to a smaller number of parameters, and yeah, and make sure that it fits on single GPU. Here you have, like, after you shrink it, you have two options. First is you can just add it as a TorchBench dependency using pip install or git some module, and then initialize it with random weights. Right? It's also fine to add model checkpoints, but we need to go through some reviews to make sure it is it will work on our setting. The second choice is you could also pickle the model, but this is kind of discouraged because a pickled model is kind of frozen. It doesn't update with the code change. So we still prefer you take choice one. Yeah, and the second step is to generate model inputs. This is the recommended way is to use some metadata, like the shapes of the input tensors. Like this should be the tensors that is already pre-processed from real inputs. This makes our work easier. But if it doesn't work, we have, for example, some jagged tensors. They are like very hard to describe using metadata. So in the second choice, we could also adopt using a single batch of some open source input data. So we can help host it on our S3 storage. Yeah, and we can pre-process it on the fly, and yeah, use them in the benchmark. And the third choice is kind of not recommended. Like we can only use it when it's just first two options are not available. So which is pickle the tensors. Yeah, because if you use pickle tensors, we cannot tune the batch size anymore, and it's also kind of frozen and doesn't follow the code change. And the second contribution you could do is adding your own backend. So we provide two APIs, get module and set module. This usually is sufficient to support most of the backends, including Torch Inductor and Torch TensorRT. So this is the code snippet that you could use to add your own backend. So the get module interface will return a tuple which contains the torch.nn.module. The second return value is a set of example inputs, right? And with these return values, you can compile your model with the backend and optionally pass in some arguments to configure your backend and finally set the transformed module back to the TorchBench model. Yeah, and then we can like integrate it into the framework so that you can gain all the performance metrics you need. Yeah, and third part is TorchBench infra. So we are benchmarking all these workloads on different CPU and GPU instances. So they are kind of TorchBench CI and PyTorch CI kind of separate infrastructure, but we can use both runners in TorchBench CI and PyTorch CI. But the difference is on TorchBench CI runners, we have they all comes with some noise treatment techniques. For example, on CPU runners, we will isolate the CPUs so that the CPU cross you are benchmarking does not run any other process. And on GPU instances, we will tune the GPU frequency so that it can generate stable results. Yeah. And notably, we have both AWS runners and Google Cloud runners. And we use the action runner controller on Kubernetes cluster to do the audio scaling. Yeah, yeah. Here's also a call out that we also welcome collaborators to contribute your machine or instances into our runner group, so that you can also run your benchmark on TorchBench CI and share your metrics and results to everybody. We have some successful stories of TorchBench customers. The most important one is the Torch Inductor or PyTorch 2 CI. So they will run TorchBench models across I think both in nightly and at deep level, and they will publish the results on PyTorch Hut dashboard every day. And you can see there are neutral results, and green ones means there's speed up, and red ones means there's regressions. Yeah, besides Torch Inductor CI, we also deploy other user benchmarks, such as the CPU benchmark, which tests channels last and int8 and other experimental CPU features. We also have an optimizer user benchmark that tests. For each model, it tests different optimizers to inspire future optimizer design. And we also have a Torch TensorRT user benchmark that tests the coverage and performance of TensorRT. And they are all open source. In terms of future work, we already added initial support to multiple batch dynamic shapes. For example, if you implement a interface called get input iterator, it will return a generator that always return a new batch of inputs. But this is on a per model basis, so you need to implement the iterator for each model. And we also want to minimize the variance or the noise of the latency in eager mode, so that at least for the eager mode, we get very stable latencies, and so that it can be compared for other settings. We also want to cover some distributed components. Although our infrastructure is single GPU, still we can run the model with DTP and SDP to at least cover some distributed code paths. And finally, we want to enable like front-end inductor-style dashboard, like the one you just see, for all the user benchmarks, so that you can get very intuitive and like good-looking front ends across, like almost for free. We encourage you to try TorchBench today. It's as easy as just pulling the Docker and test a model using run.py. We call out you to submit more models into this benchmark suite and add your own compiler backends and give suggestions to the compiler backend like interface, right? And deploy your user benchmark, and so that we if you are interested, you can further push it into the PyTorch CI. And finally, we also encourage our collaborators to onboard your own hardware as the GitHub runners so that it can benefit the entire PyTorch ecosystem. Thank you. That's all for my talk, and I'm happy to take questions. Is yes, and is optional. First, the inductor CI includes not just TorchBench, but also team and Hugging Face. So it's kind of for those ones that only exist in team and Hugging Face, we do not cover them yet. But for the TorchBench side, it will cover like 100% of everything in the inductor CI. But it's your freedom to benchmark only a subset of models or a subset of configs.
I'm curious, does it cause any overhead in terms of the regional metrics? And if so, does it impact your actual regression?
By default, we do not. So first, we because our test is very fast, measuring the latency and measuring the flops and memory usage are in separate processes, so that they won't interfere with each other.
How deterministic is this pipeline? Is it very deterministic?
Sorry, by deterministic, what do you mean?
The noise is very small. If you run the same thing twice, you got the same result.
Noise treatment is still a topic. I think most of I can roughly give a level of I think about 95% of our models are below 5% noise. It's roughly at this level, but there are still a couple of models that are unstable. It really depends on models, right? We have some study on this. I think some models are noisy, partly because it has access copies between CPU and GPU, and if you copy data, you have a lot of copies, then it becomes very stable. Very, very unstable. Okay, yeah, maybe last question. It's really per model basis. So what we do is we only provide an interface that you can, which is a generator to return the next batch, and you can tune any dynamic parameters you want in this implementation. For example, you can change the batch size and the sequence length and maybe some other dynamic dimensions. Yeah. So yeah, yes, the user can decide how to generate the distribution of dynamic shapes. Okay, yeah, thank you.